A lightning detector is a device that detects lightning produced by thunderstorms. There are three primary types of detectors: ground-based systems using multiple antennas, mobile systems using a direction and a sense antenna in the same location, and space-based systems. The device was invented in 1894 by Alexander Stepanovich Popov. It also was the first radio receiver in the world. Ground-based and mobile detectors calculate the direction and severity of lightning from the current location using radio direction finding techniques together with an analysis of the characteristic frequencies emitted by lightning. Ground-based systems use triangulation from multiple locations to determine distance, while mobile systems estimate distance using signal frequency and attenuation. Space-based lightning detectors on artificial satellites can locate range, bearing, and intensities by direct observation. Ground-based lightning detector networks are used by meteorological services like the National Weather Service in the United States, the Meteorological Service of Canada, the European Cooperation for Lightning Detection, and by other organizations like electrical utilities and forest fire prevention services. Lightning detectors and weather radar are used together to detect storms. Lightning detectors indicate electrical activity, while weather radar indicates precipitation. Both phenomena are associated with thunderstorms and can help indicate storm strength. Thank you for watching. For more educational videos, please subscribe to WizScience on YouTube or visit wizscience.com.
One of the most promising tools on the horizon is phased array radar. Its rapid scanning ability lets NOAA researchers observe storms like never before. But will it be more useful for the National Weather Service? Will it result in earlier warnings for you? Let's find out what happens when forecasters go hands-on.
Still a pronounced three-body scatter spike.
The PREACE is the Phased Array Radar Innovative Sensing Experiment. We bring in forecasters from the National Weather Service, and we have them work cases, archive cases in simulated real time. And they issue warnings and update statements just as they would in the real world. So then that allows us to learn how the data is impacting their process. Is it of benefit to them? Does it increase their warning lead time?
The past couple years have been focused on tornadic storms that cause light to moderate damage. With current radar, the average warning lead time for these tornadoes is about 12.5 minutes.
What we found from 12 forecasters working events like that, their average lead time was 21 minutes. And so that suggests that having this rapid update data, say on the order of a minute, really can make a difference in getting warning out and giving people time to respond.
So far, so good. The experiment is set to continue annually and will cover all types of severe weather events. Learn more here and follow us.
The lab is unique in that we serve the nation by supporting the National Weather Service in its mission to protect lives and safe property by improving the accuracy and the lead time of severe weather warnings.
We have a legacy of radar research and converting existing technology from military to weather purposes.
A recycled Doppler radar led to the development of NEXRAD, installed nationwide in the early 90s. It allowed forecasters to see storms like never before.
Not only did we help bring that technology to the National Weather Service and to help protect lives and property, but we have continued to upgrade that technology, keep it relevant, and keep it state-of-the-art.
Recently, a major upgrade was added. Dual polarization technology takes the radar from 2D to 3D. Forecasters now know more about what type of precipitation is falling, which is very helpful during winter storms, as well as how much rain is accumulating, resulting in better flash flood warnings. The radar can also detect and track tornadoes based on debris. Looking to the future, the National Severe Storms Lab is testing the capabilities of phased array radar. Originally used by the U.S. Navy, the antenna scans the skies electronically rather than mechanically, allowing the radar to focus on a storm.
With current technology, we get a full picture or image of what is going on within a storm every 4 to 5 minutes. So it's more like a snapshot. Whereas with phased array radar, we get that picture of what's going on in the storm every minute. So it becomes more like watching a movie. So we can do adaptive, rapid scanning on the storms that matter most, being able to provide the information that's most relevant when and where it's happening.
Another advantage of phased array radar is its multifunction capability, providing weather and air traffic information simultaneously.
Number one, it is a system that promises to replace and expand upon the existing weather surveillance radars. Secondly, to replace aging air traffic surveillance radars. And number three, it offers a potential application to meet Department of Homeland Security and defense requirements for identifying and tracking non-cooperative aircraft. With the replacement of all these various radars with a single system, the American taxpayer could realize substantial savings in cost.
You have a lot fewer radars to maintain, and the electronic capability of this also reduces maintenance costs because you do not have moving parts.
Not too long ago, the ability to predict severe weather was thought to be impossible. During the past several decades, research conducted at the National Severe Storms Lab has developed life-saving tools like Doppler radar. We've progressed from no warning of threatening weather to about a 15-minute lead time, and current research promises to extend that much further.
Our knowledge of severe storms and how they behave, and our use and ability to use the Doppler radar technology is in a lot of cases a direct result of that close working relationship, that research to operations component that we get between the National Severe Storms Laboratory and a forecast office.
That history and understanding of how these data can be used by our users and doing the research to help advance the use of radar technology, really it's what we live for, it's in our lifeblood, it's in our history.